Moin Moin, or in other words, welcome everybody to this session on charts, design and interaction. I'm Christian Tominski from the University of Rostock in northern Germany, and I will be the host for this session. In this session, we have four really exciting papers. And when I say exciting, I really mean exciting. We will hear about the latest advances in continuous color maps, parallel sets, interactive lenses, which is my favorite, and line rendering. But before we start, I would like to thank the sponsor of the session, which is Tableau. So many thanks to Tableau for supporting us. And now let's start with the first talk. The talk will be given by Pascal Nardini, and he will talk about improving continuous color maps. Pascal, please.
My name is Pascal, I'm with the Leipzig University, and today I will tell you something about our work, Automatic Improvement of Continuous Color Maps in Euclidean Colorspaces. In Chapter 1, I give you an introduction and tell you a little bit about our motivation. Color mapping in scientific visualization is one of the most common methods for scientists to gain insight into their data and communicate their research. The color map choice can have a large impact on the effectiveness of a visualization. If someone wants to create a color map, there are several empirical design guidelines that have been suggested and motivated throughout the literature on color maps. A rigorous collection from Bujack et al. Showed that the most important ones are uniformity, discriminative power, order, and smoothness. The problem that we want to address with our work is that these guidelines are usually only applied in an intuitive fashion. But why? One reason is these design rules are partly contradictory. A user would have to find an appropriate compromise based on the visualization goal. Second, the theory is not sufficiently developed to use a purely algorithmic approach. Algorithms have been suggested to make a color map locally uniform and smooth, but to the best of our knowledge, there are no algorithms available from the literature that improve a color map with respect to any of the other design rules. Third, there are no openly available tools for the application of any of these rules. In this work, we address the last 2 points. The first one is part of the future work, more on this later. We present algorithms that are able to transform a color map into one that performs more efficiently with respect to one of the specific color map design rules we mentioned before. And we provide their implementation in an open source online tool, which I will also show you in one of the following chapters. But first, I want to tell you 1 or 2 short sentences for each of the 4 design rules so that everyone can imagine what is meant by these rules. The uniformity. Uniformity is a concept that perceived distances between colors are proportional to the distances of the values they present. It is important to correctly represent the structure of underlying data. A non-uniform color map may hide features in the visualization or introduce artifacts. The order. Order is a concept that an observer should be able to order the colors that the color map traverses so that he can identify which values are higher or lower. For example, grayscale colors can be placed in a consistent perceptual order from darker to lighter. The discriminative power can be thought of as a contrast in the visualization. It is described as a number of just noticeable differences traversed by the color map. Greater discriminative power means greater ability to see details in the data, because you can distinguish more different colors. And at least smoothness. Smoothness is the absence of sudden bands in the path of the color map that cause artificial bands in the visualization. In this color mapping of a saddle point, it causes a visible X. We provide the following implementations of all mentioned design rules in the open source project CCC tool. The CCC tool is an online tool for color map design, analysis and testing. The tool is available under ccctool.com. It uses its own color map specification, short CMS, to build its color maps. This structure consists of keys which have a reference value and define the color process of the resulting color map. These keys allow discontinuous transition points inside of a color map and also the definition of areas with a constant color. So for our optimization algorithm, we search for continuous section in the color map and apply the algorithm on each of these sections separately. And finally, we can start with the algorithm chapter. First, a few general information. For each of the different evaluation rules, we introduce both a local and a global optimization. All of the following algorithms are designed for an optimization in the Euclidean space. Applying the following optimization methods can cause key color movements outside of the selected interpolation color space. In such a case, it is necessary to apply a clipping method. As the CCC tool is designed to handle only RGB possible colors, we implemented an RGB clipping regardless of the selected interpolation color space. In practical applications, the true optimum is usually far away from the input color map and not at all what the user wants to obtain. We allow the user to select a subregion of the color map for the optimization, which leaves the remaining parts unchanged. Further, in order to get a customized result, we offer the user a slider to obtain an interpolated map between the original CMS and the optimized CMS. A color map suffices uniformity if the speed of a color map is constant. Constant speed means that the perceived distances between colors are proportional to the distances of the values they represent. Our first algorithm addresses the optimization of the local speed. That means that we want to reach constant speed between each key pair. This can be reached by an adjustment of the key color or the key position. We choose to develop an algorithm that moves the keys to a position in regards to the color difference. Here is a little example. We have here two local key pairs. One has a speed of 2 and the other has a speed of 4.5. We don't want to change the colors, so the color different values delta E are fixed, and we can determine a right position so that both key pairs have the same speed of 10. This technique is very simple but also very helpful, because modifying a color map by hand to obtain a local uniform color map is very frustrating and time intensive, especially if you have a color map with many key colors. For the global uniformity, we also want a constant speed. Different to the local uniformity, we do not only check the speed of key pairs, we need to reach a constant speed for all key combinations. In a Euclidean space, that means that global uniformity is equivalent to a straight line. So we cannot achieve this by adapting the key positions like at the local uniformity. We use a linear regression to change the colors of the keys in order to get such a straight line. And we also offer the option that the user can set the start and the end key color as fixed color, so it will not be changed. I better show it with an example edit tool, so let's switch the window. Here you can see the edit page of our tool. I choose the color map that is far away of a straight line. You can see that here in the 3D path plot, and the key colors are well spread over the lab color space. And if we switch to the analysis and select the global speed plot, you can also see that the color map is not globally uniform. We want to change that and go to the optimization mode, and here on the left side you can see the different algorithm. The uniformity algorithm is already selected and we choose the global one. The Analyst tab will automatically select the global speed plot, and yeah, if we change now the degree slider, you can see here in the right top corner how the color map will move from the original color map to the result of our linear regression. And if we set a degree of 100%, we reach the global uniformity here on the global speed plot. We can do that again with a fixed start key, and now you can see here the start key color will not change if we move the degree slider. And in this case, we cannot reach a global uniformity with a fixed start key because we are here on the border of the RGB possible colors, and it will do an RGB clipping here. Yeah, and now we move back to the presentation window. The next guideline on our list is the order. We offer algorithm for the intrinsic order and the legend-based order. Let's begin with the intrinsic order. Intrinsic order is satisfied if the perceived distance between 2 points in a color map is larger than the distance to any point between them. For the local intrinsic order, this only must be achieved for all colors between 2 directly adjoining keys, and for a global one, again with all key combinations. So let me explain the intrinsic order with this simple 2D sketch on the right side. We use the distance between Ci and Ck as radius and draw a circle around Ck and a circle around Ci. Of course, in the 3D color space, this would be spheres and not circles. The intersection volume of these two spheres with a shape of a UFO is the area where a color Cj that lay between Ci and Ck would fulfill the intrinsic order. In our sketch, Cj is not located on this area and does not fulfill the intrinsic order. So let me explain how our algorithm would solve this problem. The idea is that we want to find the closest point to the original position that also fulfills the intrinsic order. Such a point would lay on the surface of one of the both spheres. To find this point, we calculate 2 straight lines between Cj and Ci and Cj and Ck. Then we calculate the intersections of these lines with the related sphere and use the nearest point that also fulfills the intrinsic order as new position. After applying and rethinking about this first idea, we differentiate between the following cases to solve the intrinsic order optimization. In the first case, Cj is located inside of one of the spheres. Then we only need to determine one straight line from Cj to the sphere center of the other sphere. After the calculation of the 2 intersection points, only one will fulfill the intrinsic order. In our sketch, this is the one at the black cross. And then we can use this intersection point as new position for Cj. At the second case, Cj is located outside of the sphere. Here we need to determine both straight lines like mentioned before, and the number of intersection points that fulfill the intrinsic order give us 3 further cases. In the case with 2 intersection points fulfilling the order, we have to choose the closest point as new position for Cj. When only one intersection point is fulfilling the intrinsic order, it is easy. Of course, we choose this point as new position for Cj. We have a little bit more trouble with the last case. There we have no intersection points that fulfill the intrinsic order, and we need a new solution for this situation. So the idea in this case is that the closest point lay on the intersection circle of the both spheres. In our 2D sketch, it would be the nearest peak of the Zeppelin shape. But how can we get this position? First, we determine a point M that is located in the middle between Ci and Ck. Then we calculate a plane with the normal vector that shows in the direction of the vector from Ci to Ck. And we use the same direction vector to determine our lines through Cj. And can now calculate the intersection point of this line with the plane. This intersection point is our first new temporary position for the J, and now we calculate the distance h from the point M to the intersection circle of the 2 spheres or the Zeppelin peak in 2D. With this information and the vector from the point M to the new Cj position, we can determine the final position for the J that also fulfill the intrinsic order. And again, I want to show this on a little example. I have here the simple CMS with 3 key colors, and the blue color is definitely out of the intrinsic order. And I have to say, if someone would give me the 3 key colors, I wouldn't be able to sort them in order. So we go to the optimization and select the intrinsic order. And we can see here in the order plot that the red bar shows us that the blue color is out of the intrinsic order. If we now change the degree slider, we can see that the algorithm moves the blue color closer to the other two. If we set the degree to 100%, the second key fulfilled the intrinsic order. And now I would be able to say, hey, it goes from gray to the gray-blue and then to the green. Next is the legend-based order. This order allows an observer to interpret which color represents higher or lower values by using the color legend. The legend-based order is violated if a color map includes a color more than once, or it uses colors which an observer cannot differentiate from another color in the color legend. Below you can see a simple example with 2 color maps, and both using a red, black, blue gradient. At the left color map, the red and the blue colors are very close to gray, and an observer couldn't interpret these colors in the color mapping, even if he consulted the color legend. On the right side, we pushed these 2 colors away from each other, and we restored the legend-based order. And this is exactly what our optimization algorithm should do. To reach that, we offer the 2 options to use the color difference or the speed for this task. The distance version pushes points away from each other independent of their respective control points, while the speed-based version will repel points further if they correspond to farther apart values in the data. We give the user an access slider so he can control the minimum distance or the minimum speed that should be reached in the color map after applying this algorithm. We begin again with the local algorithm. Here neighbored key colors should have the user set minimum distance or speed. To reach that, we implemented an algorithm that is inspired by the force-directed graph algorithm from Fruchtermann and Reingold. This algorithm has several iterations, and at each iteration, forces are affected on the graph nodes. Over the time of the iterations, the algorithm loses energy and the forces get weaker. For our variation of this algorithm, we use 2 forces. An origin force that wants to push the nodes back to its original position, and a repulsive force that pushes 2 nodes apart if they have a too small distance or speed to each other. The degree slider of this algorithm is the ratio between these 2 forces. So if the slider is on 100%, there's only the repulsive force, and if we set a degree of 0, then there's only the origin force and nothing will happen. At the global legend-based order, not only neighbored key colors can disturb the order. Here we need to search for self-intersections of the color map path, or rather we're searching for path segments which are closer than the user set minimum distance or minimum speed. And if we found such a break of order, we need to push both path segments away from each other. To reach that, we modified the repulsive force of the local legend-based order algorithm. We check if non-adjacent edges of the graph are too close together, and if this is the case, we add opposing forces to the nodes of both edges. This new repulsive force has a little problem. If you take a look to the right image, you can see 2 examples. On both, the node B is too close to the edge CD. In the upper example, this is no problem, because the node B is part of the edge AB, which is also not neighbored with the edge CD. Here the new repulsive force will solve the problem. At the other example, this is not the case, and the current state of the algorithm would not solve the problem. Therefore, we add an extra repulsive force, which only affects the graph end nodes, Here we check the end node with the adjacent edge. In case of an order break, the force will apply it on the end node and the both nodes of the adjacent edge. The discriminative power is described as a number of just noticeable differences that are traversed by the color map. The local discriminative power can be achieved through neighboring points repelling each other, and the global discriminative power through all points repelling each other. Maybe this sounds familiar to you, or I hope so, because the just mentioned algorithm of the legend-based order does exactly this. So we just use the same algorithm for the discriminative power optimization. Smoothness is especially challenging because there are many criteria that can influence how smooth a color map is perceived. We implemented two algorithms at the CCC tool. With the first algorithm, we want to give the user the opportunity to reach more uniform angles between the key colors. The user can set a minimum and a maximum angle, and if an angle is too sharp, we move this color so we reach the user's set minimum angle, and if the angle is too wide, we move the color to reach the allowed maximum angle. Like at the uniformity and the intrinsic order, we consider neighbored points for the local smoothness, and for the global one, all variations of the key color combinations. Let me show you an example. Here you can see a rainbow color map. It has a sharp angle at the yellow color and at a cyan color, and we want to remove these sharp angles. So we set a minimum angle, and yeah, we have removed the sharp angles. Next to this algorithm, we offer an alternative for the local smoothness that consider the colors in the color map which are located between the keys. For this, we implemented the Cadmium RAM splines as interpolation type. The splines are not part of the optimization mode in the tool. We implemented the spline interpolation next to the linear interpolation into the color map specification of the tool. At least I want to say something about the future work. With the next steps, we want to do research for algorithms that also work in non-Euclidean color spaces, so we can integrate the color metrics. Furthermore, we need to better understand interactions between the mentioned criteria in order to develop a meaningful multi-criteria optimization. Currently, we also reconstitute the CCC tool in the React framework and excluded the implementation of the color map specification into an extra Node.js library to increase the clarity of this open source project. And we also want to add the optimization algorithm of this work into the Node.js library. And this is the end of my presentation. Many thanks for your attention.
Okay, thank you very much, Pascal, for this very colorful talk. We do have 3 minutes for questions.
Thank you too for the introduction and all the technical stuff.
Yeah, and maybe I start with my own question. You mentioned
Yes.
effectiveness in the beginning of the talk. What do you expect?
Again, please. It was a little bit
okay,
not loud enough. Yes.
I restart.
Yeah.
You mentioned effectiveness of the visualization in the beginning of your talk. What do you expect? What is the impact of your optimizations on the effectiveness of a visualization?
Yeah, especially if one of my favorite things is the uniformity. So I work together with an artist, and she said to me that it was a big thing that she could do a slider and not have to move all these single colors to reach this uniformity. So maybe this is one of the biggest requirements of the four, which is the most used in the community, maybe. And so this maybe will help in applications. Yeah.
Okay, talking about applications, there's a question from Johannes. Do you think the application area for the color map, like choropleth maps or line charts, is also important for the design of the color map? And that is, can it also be formalized somehow?
Good questions.
I think the order and maybe uniform color, so you can distinguish the colors good. So for this cases, maybe it could be helpful, but yeah, I think it could be helpful. Maybe I can give an answer in the chat. Yes, sorry.
A related question. So your optimization is based purely on the color map specification. I think what Johanna meant is it not also necessary to consider the application or maybe also the data and optimize the thing more globally than just locally based on the...
Oh, yes. We designed the tool on the CMS to get application-based color maps and not data-based color maps. So maybe, for example, for weather data, where you have always the same range from 0 degrees to 40 degrees, and so you can better compare the different visualizations. So yes, that's the reason why the CMS is based on application-based color maps.
Okay, thanks a lot, Pascal. I encourage you to continue the discussion. There are more questions in the channels. So thanks again, Pascal. And our next presentation will be given by Frederik Dennig. He will also talk about optimization, but this time he will be optimizing parallel sets. Let's go.
For the introduction, my name is Frederik, and I'm going to present our paper, ParSetgnostics Quality Metrics for Parallel Sets. So let's jump right into the motivation. For the visualization of categorical data, we looked at existing visualizations, specifically for subsets and subset patterns. Here we found parallel sets, a visualization designed for subsets of categorical data. It visualizes subsets of the data by their categories with increasing granularity. This visualization shows the Titanic dataset. The granularity increases from top to bottom, meaning that the subsets get smaller and more finely grained. Parallel sets visualizations show subsets of increasing granularity, level by level, following the illustrated flow. In the following, I want to explain this with the example of the Titanic dataset by Dawson. This is a fully categorical dataset with 4 dimensions called survived, sex, age, and class. At the very top, we can see the ratio of survived and perished persons. On the second dimension axis, from the top, you can see the ratio of male and female people on the Titanic. On the third, the ratio of children to adults. And finally, on the bottom, the sizes of the individual classes, such as first and second class, and also crew. By looking at the first level, the ribbons between survived and sex show all 2-dimensional subsets of these categories. The connecting ribbons visualize the size of these groups: females that survived, males that survived, females that perished, and males that perished. On the second level from the top, we can see all 3-dimensional subsets. The 2-dimensional subsets are split further, now also including the age dimension. This yields a total of 8 ribbons visualizing the 3-dimensional subsets. Finally, on the third level, we have the 4-dimensional subsets of all dimensions of the Titanic dataset, by also including the class dimension. On the lowest level, we have a total of 24 ribbons visualizing 24 subsets. However, parallel sets visualizations can suffer from clutter. Some category and dimension orderings are easier to read. For example, the visualization on the left exhibits a strong zigzag pattern, making ribbons harder to follow. The one on the right has ribbons with a smaller slope. Especially the large ribbons that are orthogonal to the axes yield a much clearer visualizations with ribbons that are easier to follow. Observing this, we asked, can we determine the quality of parallel sets visualizations for comparison and ranking and propose candidates for exploration. This general problem is formally defined in the work by Barish et al., where they try to determine an optimal visualization configuration, here called phi, from the set of all possible visualizations by maximizing or minimizing a quality metric Q. This quality depends on the data, since not all data sets contain the same patterns, such as correlations or clusters. It also depends on the user, because a user might have specific requirements, such as color choice, compensating for color blindness. And it also depends on the task, since a visualization optimized for a lookup task can have a different layout than one that is optimized for a comparison task. In our work, we contribute ParSetgnostics, a set of 8 quality metrics which can be minimized or maximized to improve the readability of parallel set visualizations or optimize them for a specific pattern. The appearance of parallel sets visualizations depends on a variety of parameters. In the interest of time, I want to cover the 2 parameters that are most important for our work. Firstly, the dimensions can be reordered, just like parallel coordinates. In this example, we can see that the reordering of dimension axes has a dramatic effect on the appearance and readability. This results from an increase in the number of subsets early in the flow. Secondly, specific to parallel sets visualizations, the categories of each dimension can be reordered as well. In the example, we can see that a different ordering of the categories along the dimension axis results in a less readable visualization, containing many sloped ribbons and spanning the whole visualization. For this reason, we define dimension ordering dependent metrics to cover the first parameter and category ordering dependent metrics to cover the second one. Before I discuss the individual metrics, I want to take some time to describe the geometry of parallel sets visualizations. Here you can see a level of a parallel sets visualization with 2 ribbons that are crossing. We define the overlap of 2 ribbons as the intersection area of the ribbons, as you can see here in the center. The slope of a ribbon is defined by the angle alpha here on the right. This angle is also relative to the dimension axis. We also define the crossing angle delta, allowing us to measure whether ribbons are crossing at a flat or steep angle. And finally, the ribbon width. This is defined as the length of a ribbon's intersection with the dimension axis. So at first, I want to focus on the 3 dimension ordering dependent metrics. These metrics are in part inspired by ParSetgnostics, by Dasgupta and Kosara. ParSetgnostics are a quality metric set for parallel coordinates. Parallel coordinates is a visualization similar to parallel sets, but focused on numeric data. The first dimension ordering dependent metric is the number of ribbons. For this metric, we measure the number of ribbons relative to the number of all possible ribbons. We do this to allow for comparability, since parallel sets visualizations do not visualize empty sets. A high number of ribbons increases the likelihood of sloped and overlapping ribbons. This effect can be observed here in the Titanic dataset. However, since the ordering of categories is not affected, there are still many configurations available with a better category ordering. These metrics serve as a starting point to determine a useful dimension ordering, which is later optimized. The second dimension ordering dependent metric is the ribbon width variance. For this metric, we measure the variance of all ribbon widths. A uniform ribbon width avoids very thin ribbons. These ribbons can easily be hidden by larger ones. This effect can be observed in the example of the Titanic dataset, where a low ribbon width variance yields overall larger ribbons, which improves the readability. A high variance shows a lot of small ribbons. From this, we conclude that the low ribbon width variance is preferable. The third dimension ordering dependent metric is mutual information. This metric measures the average mutual information of neighboring dimension axes. It was first proposed by Chen. Mutual information measures the dependence between two variables, in the case of parallel sets, two neighboring dimensions. Enforcing a high mutual information orders dimensions such that dependent dimensions are neighboring. Thus, high mutual information is preferable. However, since the ordering of categories is not affected by the rearrangement of dimension axes, there are still configurations left with a better category ordering. Thus, mutual information can serve as a first step for optimizing a parallel sets visualization. Now I want to focus on the 5 dimension ordering dependent metrics, which are specific for parallel sets. As the name suggests, we optimize the ordering of categories on the dimension axis to reduce clutter and improve the readability. It is also the more flexible parameter compared to the dimension ordering. However, it is also more complex because of the large number of possible configurations. The first category ordering dependent metric is overlap. For this metric, we measure the overlap of ribbons relative to the plot size, allowing for comparability. Overlapping areas are harder to interpret since crossing ribbons are harder to follow. Even more important, bigger ribbons can easily hide smaller ones. In the example of the Titanic dataset, we can see that with decreasing overlap, the appearance is significantly cleared up, while a high overlap reduces the readability by introducing clutter. The second category ordering dependent metric is slope. For this metric, we measure the average slope of all ribbons. The slope is determined by the angle alpha. Highly sloped ribbons get thinner and longer and are thus harder to follow, which is due to the geometric properties of parallelograms. These kinds of ribbons are also spanning a larger area of the visualization. For example, in this Titanic dataset, we can see that with decreased slope, it is more readable, while a high slope enforces a zigzag pattern that reduces the readability. The third category ordering dependent metric is orthogonality. This metric leverages the slope metric, but enforces a close to perpendicular angle to the dimension axis. The slope is still determined by the angle alpha. However, we enforce an angle of 0. This enforcement of a perpendicular angle creates ribbons that are clear rectangles, which reduces clutter. In the example of the Titanic dataset, we can see that high orthogonality clears up the parallel sets visualization, while lower orthogonality shows a lot of slightly sloped ribbons, decreasing the readability. The fourth category ordering dependent metric is the number of crossings. For this metric, we measure the absolute number of ribbon crossings. A high degree of ribbon crossings can lead to visual clutter, making ribbons harder to follow, which is also linked to the increased overlap and also sloped ribbons being present in the visualization. In the example of the Titanic dataset, we can see that the low number of crossings improves readability, while a high number of ribbon crossings decreases the readability. The fourth category ordering dependent metric is the crossing angle metric. For this metric, we quantify the average crossing angle of crossing ribbons for parallel sets visualizations. Here we use the angle delta to determine the crossing angle. A high average crossing angle makes ribbons easier to follow, while a flat angle makes ribbons harder to follow. This effect can be observed in the example here, where a low crossing angle creates more close ribbons, while a higher crossing angle separates them. Now I want to talk about the evaluation. To evaluate our quality metrics, we reconstructed 5 datasets from their parallel sets visualizations in published papers. These visualizations address tasks from a variety of domains, such as property sales and linguistics. These existing parallel sets visualizations serve as a suitable target for comparison. We calculated all quality metrics for all possible configurations. We also performed a correlation analysis, which shows that all metrics are independent and measure indeed distinct properties. To evaluate all metrics individually, we performed a single metric optimization using the dataset of Ahsan et al., which is analyzing the security and cost of data storage, determining the location where data storage should be bought with a high security level. We found that this published parallel sets visualization is improved by all metrics except one. The overlap metric improves the dataset by 81% in terms of overlap, and similarly the slope and crossing angle, which improved the visualization by 70% in terms of overlap. We also applied our metrics to parallel sets visualizations with curved ribbons, which is taken from a publication by Rogers et al. The task for this visualization is to present the result of a human-computer interaction study. And here we are considering, again, overlap as a measure of degree of clutter. The slope metric reduces clutter by 51% and the crossing angle metric by 45%. In comparison, the overlap metric itself yields a 51% improvement. This shows that our metrics can improve parallel sets visualizations by optimizing just one individual metric. To evaluate the effectiveness of our metrics in a multi-step optimization, we performed a multi-metric optimization. First, we selected dimension ordering that 2 out of 3 dimension ordering dependent metrics agree on as being optimal. As a second step, with a fixed dimension ordering, we choose a parallel sets visualization according to the metric that improved the most compared to the original visualization. We perform this optimization using the visualization in the publication by Ko et al., dealing with property sales analysis. First, we analyzed the dimension ordering. The number of ribbons and the ribbon width variance yield the same dimension ordering, while ribbon width variance is reduced by 12%. For the category ordering, we fix the dimension ordering accordingly. Now we can observe that the orthogonality and number of crossings yield identical visualizations. By assessing the crossing angle, reducing its value by 15%, and choosing the overlap as an objective measure for clutter, we can see that clutter is reduced by 1%. Observing the result, we can also see a cleared up top level compared to the original. For the visualization presented by Rogers et al., we perform the same series of steps. The number of ribbons and ribbon width variance provide the same dimension ordering. Thus, we only consider a dimension layout with this ordering. To determine the order of categories, which influences the appearance of the ribbons, we find that the optimum of overlap and slope have the same dimension ordering, as suggested by the dimension ordering dependent metrics. The visualization suggested by slope reduces the clutter by 53%, considering overlap again as the objective measure for clutter. This visualization focuses all splits and crossings on one half of the visualization, in this case, the left. I want to cover the results of our correlation analysis briefly. Here we found that no metric correlates with any other metric for all analyzed datasets. This shows that all metrics are independent and measure distinct properties of the parallel sets visualizations for the generated datasets. Before I conclude, I want to present some future work. We are planning to perform a user study targeting general tasks, such as lookup and comparison tasks. in order to determine whether some metrics are better suited for different tasks than others. We also plan to address the optimization for different dataset characteristics, such as cases where many small categories or few dimensions are splitting the dataset into many small subsets. In this case, we also plan to verify the exhaustiveness of ParSetgnostics. Apart from a user study, we plan to improve the complexity by assessing the properties of our metrics and derive a reordering algorithm, such that we do not need to consider all possible configurations of a parallel sets visualization. So to conclude, in our work, ParSetgnostics quality metrics for parallel sets, we contribute 8 quality metrics that allow for the comparison and ranking of parallel sets visualizations to reduce clutter and improve their readability, such as overlap, slope, orthogonality, and the number of crossings. We formalize the geometric properties of parallel sets visualizations, which we use to later formalize and describe our quality metrics. Also, we compare our improved parallel sets visualizations to published ones. Our results show that ParSetgnostics facilitates multidimensional data analysis of categorical data by providing optimized parallel sets designs with reduced clutter of up to 81% compared to the initially proposed parallel sets visualizations. Thank you for your attention.
Okay, thank you, Frederik, for this very categorical talk. And thanks to your optimizations, we have 5 minutes for questions. Michael asked, based on the quality metrics that you have seen in your experiments for parallel sets, would you say that this visualization type is more useful for certain tasks than others?
So I would say yes, definitely so, especially for seeing the relationship between dimensions. So having a comparison task, this visualization is better than others, I think. In terms of tasks, we are trying to focus more on that in terms of our quality metrics. So which quality metric is more useful for which task here. So having another optimization in terms for given tasks is our goal also.
Okay, and there's one more question from Johanna. She's a little bit surprised that the metrics for crossings and overlaps are completely independent. Why is that the case?
Yeah, so we found that this is data set dependent, so that there are data sets where all configurations have a relationship in terms of crossings and overlap, but that's not the case for all data sets. So we think that this is the case because the ribbon width is very different for a data set where there are a lot of very small subsets. And in this case, then the overlap is not so important with respect to the crossings, and then there is this difference in terms of correlation.
Okay, then maybe I ask one of my own questions. When you are reordering the dimensions and the categories, you assume that they are independent. What about when there is a semantic meaning, like in ordering? For instance, in the Titanic dataset, you have first class, second class, and third class. And can you treat this or maintain this ordering of the categories, or even if you have orderings or semantic meaning in the dimensions?
Yes. So if the data set demands or it is useful for the domain that the ordering is persistent for all configurations, we can fix the ordering for the specific dimensions and still calculate our quality metrics for changing the other variable dimensions, basically, and this is still viable for all quality metrics.
Okay, and we have one more question from Hayan. Is there a priority of metrics to use in multi-metric situations? And how do you decide which metric to look at first?
Yeah, so for the multi-metric optimization, we basically use the dimension ordering dependent metrics for an initial look at the quality or ordering of dimensions, just so we can reduce actually the number of configurations we look at. So that is the reason we look at those first, and then we optimize in terms of category ordering. And yeah, where there is more flexibility there.
Okay, so and maybe my last question is, in the beginning of the talk, you mentioned that the optimization is dependent on the data, the user, and the task. And I guess your metrics are dealing most of the data. How would you integrate the user and the task?
Yeah, so this is what we are actually want to address in future work, where we actually have a look at our quality metrics and how they fare in the user study, where a user performs a specific task, for example, comparison task or a lookup task, and see if there is a metric that is more useful for a given task. Currently, we are just addressing the data, having a look at, basically the properties of parallel sets as they are.
Okay, so there are more questions in the chat, but I think we have to continue. So let's thank Frederik again. So now, after 2 talks on computational improvements and optimization, we move on to enhanced interaction. And next, Moonisa Ahsan will talk about a new approach for exploring data with interactive lenses. Moonisa, we are looking forward to your talk.
A virtual hello to everyone. I'm Moonisa Ahsan, co-author of the paper on a very interesting topic, that is, a novel approach for exploring annotated data with interactive lenses. Visualization has become an established mean to help people in various fields to gain insight into their data. Visualization is, however, an interactive process in which users construct their understanding through data and visualization parameter exploration. Interactive visualization lenses are an important class of methods to support interactive multifaceted data exploration. The general concept is to provide alternative visual representations for selected movable regions of interest of a display. Due to their flexibility, they are among the most widely used techniques in scientific and information visualization. Lenses maintain visual attention in their interior, letting users focus on the data currently under analysis. While the surrounding-based visualization serves as context, providing location awareness, while helping users to understand relations between the altered and the base visualization. Dozens of different techniques have been presented for defining various lens effects to solve specific visualization problems. In this work, we focus instead on defining user interface mechanisms to support effective navigation strategies based on lenses. In particular, we introduce techniques to support effective focus and context lens and camera motion, and to guide users inside an annotated dataset. Let's have a quick teaser of our approach. Our first key contribution is a novel user interface to jointly control lens and camera to support effective focus and context exploration. Our second contribution guides the users in discovering interesting areas while navigating with the lens, suggesting annotations and displaying them without introducing clutter. Our contribution is at the crossroad of 3 different areas: interactive lenses, guidance, and annotations. I refer you to the paper for a detailed analysis of the related work. Here, I will only and briefly mention the main concepts we are building on. Interactive lenses offer support to overview and detail, focus and context, and cue-based techniques. The vast majority of the literature mostly focuses on defining effects to solve visualization problems. The recent survey of Tominsky, for instance, cites over 50 different techniques. Work on interaction were especially developed for multi-touch interfaces, for instance, to create or delete lenses, manipulate their geometry, or parameterize operations. The control of lens position and scale has been treated so far, especially related to lens magnification. Our work introduces instead new ways to jointly control the relative positioning and scaling of the focus and context areas. Guidance approaches built on intelligence services that collaborate with users to solve tasks. While early work focused on assisting human-computer interaction, guidance research has recently started to target information visualization. The recent survey by Seneda and colleagues highlights how existing approaches mostly support the interpretation of visualization. Our technique, instead, aims to assist direct interaction during an analysis task. We do so by combining camera and lens motion and by directing users toward annotated areas. Several authors have also proposed to guide users towards interesting areas, for instance, by controlling the camera, creating animation paths, or defining video tours. The work of Balsa is the most similar to our approach, since it selects a viewpoint at a time based on a scoring system, expanding works previously done in the area of graph exploration. None of these approaches, however, target lenses. In our work, we assume that the data under inspection has been enriched with annotations that visually mark areas of interest in the dataset. Finding relevant annotations and presenting them in a comprehensible way without cluttering the display, however, is known to be very challenging. In addition to letting users explicitly enabling or disabling categories in the interface, the techniques proposed in the literature deal with overcrowded displays by modifying the appearance, distorting the image, or using space-time trade-offs. Lenses have also been used to reduce congestion, for instance by using intelligent sampling inside the lens. These methods do not target overlay images draped over surfaces. Haspe and colleagues focused on that problem, but assumed non-overlapping annotations. In our approach, we use both temporal and appearance modification techniques by selecting one annotation at a time and exploring it with the lens. Now, let's look at our first contribution concerning focus and context lens and camera control. Real-world datasets typically have spatially attached information that appears at widely varying location and scales. Exploration using lenses requires users to continuously switch between complex gesture combinations for selecting areas of interest by moving the camera and controlling, scaling, and positioning lenses to perform inspection. Maintaining an effective focus and context visualization is difficult. Switching user interface and mental modes increases cognitive load. We solve this problem by jointly adjusting camera and lens parameters in response to user actions. The focus and context condition is verified when the lens is large enough to show a good amount of data inside the focus area, and is positioned so as to leave enough surrounding context to interpret the lens content and avoid getting lost in the dataset. When the user acts on the lens to move it or scale it, we modify both the camera and lens parameters to ensure that the condition remains satisfied. Scale and position of the lens and the camera are thus linked and can be easily controlled by simply dragging or zooming actions on the lens. When the user explicitly acts on camera, the lens must remain anchored to the object because it should maintain the selected focus area. If we leave the focus and context condition, the controller switches to standard mode by decoupling camera and lens parameter adjustment. If the focus and context condition is met again, the controller switches back to focus and context mode by automatically adjusting camera and lens parameters in response to user actions. Our joint controller allows users to better concentrate on their analysis tasks. As seen in the video, at the core of our technique is thus the detection and enforcement of a focus and context condition. We do that by finding the proportion between direct lens motion and camera motion that best matches user input while meeting the constraint. First of all, we make sure that the lens is not too big or not too small. This is done by zooming in with the camera. when the radius of the lens becomes smaller than 10% of the visible size of the dataset, or zooming out if it is larger than 20%. Once we have ensured that we have a reasonably sized lens in screen space, we make sure that after motion, the center of the lens doesn't go outside the dataset, and at least half a radius of the context is visible in the viewport in all directions. When the lens is in the central part, the user input maps almost only to lens parameter changes, and the lens follows the user. When the lens is at the boundary and moving towards it, the lens remains fixed in the screen space, and the camera moves in desired direction. In between these two extremes, we smoothly interpolate between these two behaviors. As a result, the user can fully explore the dataset while just controlling the lens, without any mode switch and never leaving the focus and context condition. We performed a user evaluation for assessing whether the proposed joint controller provides advantages with respect to the classic controller separating camera and lens motion. All our tests were performed in a web-based setup. People were asked to place, as quickly as possible, their lens over a target lens at the proper position and scale after seeing an image of the surrounding of the target. The tests were repeated, presenting the two interface versions in randomized order. The case study included 25 participants, 14 males and 11 females, with the ages between 11 and 69 and the median of 41 years. The analysis of performance results reveal the median completion time for all users. Using the standard interface, it is almost 90 seconds, whereas it is 52.34 seconds for our controller, leading to a 42% improvement in performance results for our approach. The smaller interquartile range and lack of outliers reveal that lens and camera controller also provides a more homogeneous performance. ANOVA further confirms a significant effect on completion time with our approach. We also carried out an usability evaluation using the System Usability Scale questionnaire. Our joint controller had a good score of 79.6, which is ranked as good, versus the lower score of 65.7 for the standard controller. The ANOVA results confirm that there was a significant effect on usability score for the two interfaces. Individual questions analysis demonstrated a significant effect favoring our controller on the perception of integration, consistency, complexity, ease of use, and desired frequency of use. This is very likely due to the frequent model switches imposed by the decoupled controller, which leads to confusion. Now, let's move on to our second contribution on assisted and automatic navigation in an annotated model. Navigation is further assisted by exploiting data annotations. At authoring time, interesting areas are annotated and all annotations are stored in a database. In addition to traditional visual markups and information links, we associate each annotation with a lens configuration that highlights the region of interest. We can also see the amount of clutter if the annotations would be displayed together. During interaction, an assisting controller determines the next best lens in the database using a scoring system based on the current view and lens parameters and the navigation history. Here, we see all the database annotations colored by score. Red represents high relevance to the current lens. The assisting controller runs in the background while the user is moving the lens and identifies the best lens based on a scoring system detailed in the paper. When the controller finds it, it decides how to display the associated annotated area in a context-dependent way. If the selected lens is similar enough to the current lens, it is directly displayed. This happens, for instance, when hovering over an annotated area. When the user moves away from that area, the assisting controller restarts looking for other possible annotations. Since only one annotation at a time is displayed, clutter is avoided. Far or very different lenses are instead suggested to the user only if enough time has passed from the last shown annotation or if the user explicitly asks for suggestions. An animated glyph shows the annotation preview and the direction in which the annotation is located. The lens is enriched with simple interactive buttons to accept or reject the suggestions. If the user accepts the suggestion, the system smoothly interpolates the lens, its content and rendering parameters to the proposed annotation. Fully guided tours can be started at any time by telling the system to automatically accept all suggestions. As seen in the video, the scoring system is thus the basic component of our guidance approach. Ideally, a good scoring system should have several characteristics. First, it should favor the annotations that are closer in position and scale of current lens and limit the visual and semantic changes. Secondly, it should consider authoring information by favoring high priority annotations marked by the user. And finally, it should observe navigation history to avoid repeated suggestions if other information is available. We reach this goal by modulating spatial and similarity scores with the authoring importance and a history weight. The spatial score is proportional to the proximity of a stored lens in the database with respect to the currently active lens. It is computed by summing lens overlap, that is non-zero when the lenses share same area, along with context overlap, it's non-zero when the two context regions partially intersect each other, plus the location similarity, that is non-zero also when the two lenses are far from each other. For computing overlaps, we used Jacquard distances, that is intersection over union, while for location similarity, we used an exponentially decreasing function of travel distance. The content similarity score, instead, is an application-dependent measure of how similar the area inside and outside the lenses are in terms of content. For this paper, targeting annotated stratigraphic models, we flag a significant change if the current and target focus and context areas differ in displayed layer and/or annotation class. These changes were weighted by the relative size of the affected areas. The history score instead assigns a temporal weight assigned to each viewed annotation. If an annotation has never been seen or the annotation disappeared a short time ago, the weight is set to 1 to make the annotation reachable. As time passes after the annotation disappears, the weight slowly fades towards 0 to make the annotation less likely to be reselected. Finally, after some time, the score increases again to return to the initial condition. The total score that guides annotation selection is thus a weighted sum of lens score, context score, and semantics score, scaled by the static authoring weight and the dynamic history weight. The relative weights of the spatial and context score terms allow us to tune the sensitivity to geometric and semantic changes. In this paper, we did not tune these values and set them all to 1. We performed a user study to assess the effectiveness of our approach in a use case in the cultural heritage domain. All our tests were performed in the same web-based setup and with the same participants as in the previous study. People were asked to explore at their own pace an annotated sculptures dataset. They used 3 different interfaces, our assisted navigation, and 2 options using thumbnail bars to select target annotations. The tests were repeated, presenting the 3 interfaces in randomized order. On average, with our assisted navigation, a user viewed almost 25 suggested annotations in each session, compared to fairly lower rate of 17 and 18 annotations in other 2 interfaces respectively. ANOVA results confirm the significant effect on number of viewed annotations. With our controller, 82% of the proposed suggestions were accepted, showing the relevance of the scoring system. Moreover, significant time was lost with the other two controllers during interaction with the bar and not the models, hence reducing the focus on the exploration. Regarding anomalies, extreme behaviors were also present with the thumbnail bar version, including not using the bars at all or using them as only interaction methods. We also performed a usability evaluation that showed a marked preference to our controller with an excellent score of 85.4. The ANOVA results confirmed that there was a significant effect on SUS score for these interfaces. ANOVA on answers to individual questions revealed significant effects on the perception of complexity and awkwardness, desired frequency of use, and the amount of training perceived to be required. This is of particular importance for museum applications in which walk-up and use interfaces are paramount. So, to conclude, our work has introduced two contributions: a joint lens and camera controller to support effective focus and context exploration, and a guidance approach for exploring visually annotated models with the lens. Results are good and encouraging. Our future work will concentrate on enhancing lens movement and control by exploiting velocity measures, and on improving exploration of annotated models by taking into account relations between annotations and not only between annotations and the model. We also plan to study extensions of our work to 3D datasets. Thank you very much for your virtual presence. I'm open for questions and feedback. You can reach out to me on the given email for further discussion or queries.
Okay, thank you, Moonisa, for this very interesting talk. Actually, I have to say this is my personal EuroVis best paper because it combines interactive lenses and guidance, which are two of my main topics.
I'm very glad to know that. Thank you for having us.
We have 5 minutes for questions, and let's start with a question from Hayan. Do you have any plan to implement a 3D lens for 3D objects, for example, 3D point clouds?
I would consider the question from Hayan a very ideal extension of our future work. Well, yes, while we focused on 3D objects in our current implementation, we do think, and we definitely plan, that our methods could work on 3D objects by sliding on the surface. And this would be more difficult due to topological changes, but still we think it is very interesting to look at, and we are definitely considering ways and methods to implement this approach.
Okay, so maybe related is my question. So do you think that your approach, especially the navigation thing, will work with lenses that automatically change their size?
Okay, this is a very interesting question, and I would say that at the moment, currently, we assumed that the zooming of the lens is done by the user manually, and the rest of the context and the camera, everything follows that. So, but however, the basic idea is to adapt the camera to the changes of the lens in position and scale, to avoid usability overload for the user, and so that the user can particularly focus on the exploration part. So we think that it would be very interesting to adapt to the methods that also adapt scaling, or even the lens shape automatically. That could be a very interesting area, that the lens automatically adapts to the different shape that is not predefined, and it could be more interesting. So this would definitely further simplify the work of the user by reducing degrees of freedom, and then the user can easily manipulate and get better insights with more interesting approach of the interface.
Yeah, nice that you mentioned the shape-shifting lenses. That would be my next question. But do you think that that will be a conflict? Like the lens itself will change its shape or its size based on the data, and then you have the view transitions and the navigation of the user. Have any ideas on how you cope with this conflict?
Okay, it's a very interesting and aspect, but honestly, it's not a simple problem to address. I would think that this problem could be addressed in two different ways. First, what criteria should be fulfilled to adjust the shape of the camera, shape of the lens, and then second is how to avoid too much semantic changes while switching from the layers from each lens to the second. So I would say that even though it's a difficult concept, it can be handled in two ways. Like, of course, we have to look more on what literature says and how we can adapt to a better approach. But at the moment, currently, I would say that having a set of criterions that are met when to allow the shape acquisition of the lens, like we could keep it flexible. And the second would be in what conditions we will have the least semantic changes required. So if both of them are met, we could proceed with the change in shape of the lens. Otherwise, we could go on with the uniform approach as already shown in the demo.
Okay, thanks. I don't see any more questions, but my last question maybe is, do you think, so like I really like this guidance and that the lenses can automatically move when the user wants to have this. Do you think that this can be expanded to have an automatic tour?
Of course,
so moving from one interesting point to another?
In our opinion, that was one of the things that we focused in assisted and automatic navigation, that the lens is automatically suggesting the next best annotation depending on the current position of the lens and the layer of annotations available underneath. So if the user keeps on asking the suggestions, okay, it's manual, but even if it doesn't, it automatically suggests new annotations, and it could definitely make a very nice tour so that automatically proposes new interesting areas for focus while the user is exploring new parts of the area of interest. So yes, definitely it could definitely help that.
Okay, then thanks a lot, and also thanks for to all the co-authors for being with us, and let's move on to the next presentation.
Thank you very much.
So now for the last talk of the session, we switch back from interactivity to optimizing the visual representation, but we keep the lenses in play. Our presenter will be Thomas Trautner, and he will be talking about advanced line rendering for different types of charts. Thomas, the floor is yours.
Hello everyone. My name is Thomas Trautner, and together with my supervisor from the University of Bergen in Norway, Stefan Bruckner, we developed Lineweaver, an importance-driven order-enhanced rendering of dense line charts. And to begin with, let me start by telling you why we consider this surprisingly little explored topic of utilizing blending order and its impact on line charts to be particularly interesting. Line charts are an effective and widely used technique for visualizing series of ordered two-dimensional data points. The relationship between consecutive points is indicated by connecting line segments, revealing potential trends or clusters in the underlying data. Unfortunately, individual lines become harder to distinguish and interpret with an increasing number of lines. A popular remedy to distinguish individual lines is the use of color and standard alpha blending. Unfortunately, the blending order is currently either ignored or naively used, for example, assuming it is implicitly given by the order in which the data was saved in a file. This is common practice with standard visualization tools, such as Tableau, and as you can see here, even in PowerPoint. Due to the non-commutativity of classic alpha blending, this results in misleading and possibly even contradicting visualizations of the same underlying dataset. The terminology of the algebraic model for visualization design proposed by Kindelman and Scheidecker explicitly refers to this as so-called hallucinators. We therefore present Lineweaver, a novel visualization technique for dense line charts. Using an importance function, we developed an approach that correctly considers the blending order independently of the render order and without any prior sorting of the data. Well, you may ask, is order really that important? As indicated by the Gestalt principles, rendering order and the resulting occlusion relationship among graphical elements can have a significant impact on their perception. For example, when looking at the wireframe representation of a cube, where only the edges connecting the corner points are visible, our brain will not emphasize the individual primitives, such as triangles, rectangles, or trapezoids that arise from intersections, but instead it will tend to recognize the three-dimensional cube due to the implicitly derived order of the lines instead. Knowing that, how can we now apply these insights to line charts? I have to say, researching while wearing a warm, cozy, and if you ask me even cool-looking Scandinavian-style sweater, a so-called Mariusgenser, was actually quite inspiring. As shown here, we can easily draw an analogy to the textile industry, for example, when comparing weaving or knitting techniques. Each juxtaposition shows a classic illustration on the left in comparison to a visualization of digitally woven or knitted lines on the right. Instead of a global ordering of individual threads, they are locally interwoven, forming a visible pattern to the human observer. In the same way, our aim is to thread lines in a meaningful pattern, instead of simply pasting them on top of each other. We therefore started our research by exploring related and inspiring work that is already out there. First, I therefore want to start with visualizations of features derived from line data and how they can be visually encoded. One possibility to reduce clutter is to visualize a density estimation instead of individual lines or curves. Unfortunately, density representations in general are not well suited when analyzing individual lines, especially in sparse regions. Other work includes hierarchical cluster enhancement for parallel coordinate plots, visualizing clusters as opacity bands. But unfortunately, the used blending operator or blending order is not further specified. Assuming that multidimensional data originates from a continuous domain, continuous parallel coordinate plots represent a related approach to kernel density estimations, and therefore benefit from the same advantages while suffering from the same disadvantages. Assuming that lines or curves can also be used to view three-dimensional trajectories or networks, edge bundling can help to improve the readability of graph visualizations. And here I want to point out that we do not consider edge bundling as a competing approach, but as a possible preprocessing step. The resulting line bundles could, for example, subsequently be interwoven using Lineweaver. Resulting line bundles can furthermore be emphasized by global illumination and real-time ambient occlusion approaches, which we consider as very effective. Additional inspiration comes from combining space-time cubes with kernel density estimations, interpreting line sets as volumes. A volumetric representation allows for the use of transfer functions, which inspired us to use importance functions. Of course, there's also research related to advanced and optimized rendering techniques for dense line and curve datasets. One possibility to reduce clutter is to visualize a smooth version of the input data without high frequencies or noise, which we consider as an optional preprocessing step, being again potential input for Lineweaver. Polar stroking, for example, represents current state-of-the-art in line rendering, where the arc length can be used for texturing or dashing. We as well create the polygonal scaffolding for each polyline by extruding it on the fly into a triangle strip. Other related strategies consider the rendering of lines as a global optimization problem. Unfortunately, in contrast to three-dimensional datasets, line charts do not have such an implicit given depth order. Furthermore, I want to point out that weaving as a technique usually refers to the selection of one colored item, such as a part of a polygon or line, which is then exclusively rendered on top at a given location. Blending, on the other hand, refers to the mixing of multiple colors, for example, assigned to multiple lines which all overlap. Our approach can be seen as hybrid between both, as we use blending to combine contributions of lines with similar importances. But since importances may vary along the lines, their overall appearance may be reminiscent of a weaving pattern. Finally, I want to highlight depth-dependent halos, which inspired us as well to visually emphasize resulting weaving patterns. In summary, this and many other related papers have inspired us, and next I want to introduce you to the basic requirements of our algorithm. Our approach is based on the following three requirements. First, the contributions of individual lines should be independent of their order in the dataset or the order in which they are rendered. This way, we avoid render or blending order dependent and therefore possibly misleading visualizations, so-called hallucinators. We therefore regard a line set D of n polylines with its members L1, L2 until Ln represented as tuples of m-ordered two-dimensional points P1, P2 until Pm. The resulting parametric curve of each member is normally a polyline generated by linear interpolation between associated points. But of course, other interpolation functions are equally possible. We chose this formulation since it is general enough to represent common visualizations such as time series charts or parallel coordinate plots, which simply constitute different mappings between the underlying dataset and the x and y coordinates of the individual points. Second, line segments with similar importance contributions should also contribute similarly to the pixels they cover in the final image. This means that the contribution of line segments to a pixel that they both share are averaged, and hence the order is irrelevant. Third, when the importance of line segments differs significantly, the line segment with the higher importance should occlude the line segment with the lower importance. In our approach, we therefore propose to preserve occlusions and depth cues by using a blending operator that still exhibits occlusions while providing explicit control over occlusion relationships by introducing an importance function. While this may at first glance look like a minor semantic distinction, replacing the term order by the term importance, it opens up several interesting advantages. Our importance function now associates a scalar importance value with every position along each line or curve and has two major properties that distinguish it from order. An importance function is quantitative in nature and not just ordinal, and it doesn't need to be constant along a line, but it may vary. To achieve this, we need an adequate planning operator, performing on a per pixel resolution, which allows us to freely vary the importance function across a primitive. The decision of whether one element is in front of another in the classic over-operator is inherently binary and therefore prone to artifacts. A good illustration for this is set fighting. We therefore rely on a blending operator where the color contribution of one element influences the contributions of the other elements whenever they are within a certain importance range. We do this by using a continuous follow function. The individual contributions are then blended in sequence of their importance instead of their random order, using a conventional over-operator. These properties can be seen in a pairwise comparison of two lines, each with varying importance. A red line with a step function as importance function, a turquoise line with a sign function as importance function, and a brown line with a tent function as importance function. Note the differences between smooth and abrupt changes in importance in A, how lines are averaged when their importance values are equal or close to equal in B, and that even highly fluctuating changes are not prone to errors in C. So far, I've already talked a lot about importance and how it can be used, so it is now finally time to define importance functions and where they may originate from. In principle, there are many different ways of how importance could be defined. First and most naturally, the importance value itself may be part of the underlying data, such as confidence or the result of a feature detection algorithm. In many cases, however, such domain-specific explicit importance measures may unfortunately not be available. In this case, we may instead want to use a more fundamental property of the lines themselves. Our goal is to minimize the amount of overdraw in a heuristic manner by assigning lower importance values to those lines that take up screen space. A simple way to achieve this is by specifying the importance based on the arc length of each line. And the impact of this simple yet powerful geometric property is shown here. How can this now be applied to light charts? Or what effect does it have on, for example, parallel coordinate plots? Basis for our exploration was the benchmark dataset of Blumenschein and others evaluating different axis reordering strategies in parallel coordinates. They found that intersections of line bundles can help identifying clusters in cluttered datasets. It allows us to compare their suggestions to our insights. In other words, that the set ordering has a significant impact and that both orderings, axis and depth, are not independent. The authors conclude that this similarity-based axis arrangement, as shown here, tends to be less appropriate when identifying clusters. As illustrated from left to right, it is difficult to distinguish clusters when randomizing the order of lines, even when different colors are assigned to each cluster. This obviously does not change when lines are additionally highlighted with halos. Using a global importance, meaning an importance per polyline, the exact shape of the clusters becomes visible, even without colors. The importance of each line is determined by the cluster it belongs to. Apart from noise, the cluster with the most lines is considered as most important. Within each cluster, the importance of the line is then determined by its arc length, whereby the shortest line is rendered on top. Although the analysis of clusters using this similarity-based axis arrangement has so far been considered unsuitable, it is now done expressively using Lineweaver. Extending the idea of a global arc-length dependent importance and exploiting the fact that importance values may vary locally, we propose an approach to generate importance values for common scenarios. In this case, each line has an associate group identifier, here highlighted in color, and our goal is to reduce the amount of overdraw by assigning importances based on an estimate of the amount of screen space taken up by this cluster. To derive a meaningful algorithm, let's look at a simplified toy example. The axis values of a particular group may vary locally for one dimension, but later on may fall in a much narrower range. Other groups may exhibit an inverse behavior. In such a case, the importance value for each group should correspond to the estimated amount of screen space, such that the groups that take less space should receive higher importance values. We propose the following greedy weaving loom algorithm to compute the local importance values for such a weaving pattern. For each value along the independent axis of the graph, we first compute the minimum and the maximum value of each group. In other words, the interval on the dependent axis covered by lines belonging to this group. This allows us to determine the envelope of all lines associated with a group by connecting two subsequent intervals along the independent axis, forming a trapezoid. Next, we compute their areas. Let's narrow it down even further and take a closer look. Two scenarios may appear. First, there are no overlaps and therefore ordering them will not have an impact on the resulting visualization. And second, there are potential overlaps of the calculated cluster envelopes. In this case, we iterate over the calculated areas along the independent axis with the goal of establishing an ordering of all groups according to a cost function. Again, let's take a closer look by visualizing the math behind it. The cost value for a group corresponds to the sum of intersection areas with all other groups, multiplied by the area covered by the group itself. Initially, all groups are marked as active. Using the computed envelope areas, we next determine the area of intersection between all other active groups. Then, we select a group with the lowest cost value among the active groups and mark it as inactive. We then repeat recomputing the cost value and select a group with the lowest cost until no active group remains. The importance values are then assigned based on this sequence of selection. In other words, the first selected group receives the highest importance, and so on. To demonstrate our technique for locally varying importance functions, we use a parallel coordinate plot from the UCI machine learning repository, containing properties of cars such as origin, number of cylinders, weight, horsepower, etc. from cars produced between 1970 and 1982. As shown here, when randomized, compact clusters like the red European cluster or even more the brown Japanese cluster bundle are difficult, if not impossible, to perceive and extract insights from. When using Lineweaver instead, it immediately becomes visible that Japanese and European car models have similar low displacement, horsepower and weight, and therefore also longer acceleration times, whereas American cars cover a much wider spectrum. In contrast to the rather compact and therefore strict ordering of displacement, horsepower, weight and acceleration, when looking at the model here, for example, all three clusters are equally broad and therefore averaged instead of layered. Another well-established form of visualization are Andrews plots, which are sometimes also referred to as smooth parallel coordinate plots. Each n-dimensional data point is defined as finite Fourier series, and here you can see the result of such a transformation. If the blending order is ignored or naively used, essential visual information is lost, even if outlines and halos are added or clusters are colored. If, however, the ordering of clusters is optimized, both outlines and halos, as well as colors, can help perceiving clusters. Due to this optimization, the most compact beige cluster becomes visible. Notice how its color and opacity are averaged when it overlaps the turquoise cluster with almost identical width. A similar phenomenon can be seen with the dark blue and brown cluster. In contrast, the less compact red cluster is alternatively woven from front to back and vice versa. Each of these changes is smooth, which avoids hard cuts and discontinuities, enabling the viewer to better understand the entirety of the visualized dataset. Next, I want to present time series data derived from high-resolution satellite images, describing temporal changes of an area, considering in this example 4 classes: soy red, grassland beige, poplar turquoise, and minerals blue. Using the dataset order, classes have been saved one after the other, and are therefore perceived as individual bundles. Unfortunately, the class that was rendered first will be the least visible, and the class that was rendered last will be the best visible. With random order, chance decides which outliers are preserved or which lines are rendered last and are therefore best visible. Lineweave, on the contrary, works independently of the storage and rendering order, providing the same visual result even when these orderings are changed. Note that this time, the high smoothness of the blending guarantees that individual bundles are easy to identify, although they are mostly overlapping. Our approach also supports dynamically changing importance values, which enables various types of user interactions. To illustrate this, we implemented 2 well-established techniques: a magic lens that enables focus and context exploration, and angular brushing. The lens positioned at the mouse cursor has local influence on the importance of all lines within, and allows us to see lines that pass through a region even though they are covered by other lines. Similarly, angular brushing can help to locally pull a bundle of lines with a certain angle forward, like a rubber band metaphor. Our approach was implemented in C++ and OpenGL, and the complete source code is available at GitHub. It consists of 2 phases. During line rasterization, we upload the x and y coordinate and the importance per tuple to the GPU. Based on the desired line thickness, we construct a triangle strip that allows us to interpret each line using a signed distance function. Together with the importance value, each contribution is then added to a per pixel linked list. During fragment blending, we sort the linked list based on an importance and then use the blending operator to determine the final pixel color. To evaluate our technique, we additionally conducted performance measurements. In total, we analyzed 2 artificially generated datasets and 4 real-world datasets with different densities and varying numbers of lines. Furthermore, we used 2 representative screen resolutions and scaled each dataset so that its bounding box filled the viewport. In addition to the visual results and obvious visual differences, we furthermore attempted to numerically quantify the degree of overplotting, although there may be other measures that can access this in more detail, since our method is by no means tweaked to optimize this metric. As can be seen here, our method provides interactivity, and it is therefore easily possible to interact with it in runtime. The analysis furthermore showed that Lineweaver increases the information content by reducing clutter and overplotting, and therefore helps to display line data in a more expressive way. To conclude, I want to summarize our contribution. Lineweaver is a novel visualization technique for dense 2-dimensional line data, allowing for an optimized blending independent of the rendering order and without costly initial sorting. The basis of Lineweaver is formed by a quantitative importance function, which either originates from external data or is derived from geometric properties of the lines, such as arc length, and additionally may vary locally. Furthermore, we presented Weaving Loom, an algorithm which can be used to derive local importances. We have demonstrated that our approach can be implemented on modern GPU architectures to provide interactive and high-quality visualizations. And last but not least, I want to mention that this work was supported by the EuroVis project funded by the Research Council of Norway. Thank you very much for your attention, and if you have any questions, please feel free to ask now.
Okay, thank you, Thomas, for this really beautifully rendered presentation. I see several questions in the chat. They are mine. Maybe let's start with the sponsored question. You mentioned Tableau in your presentation. Do you think they will integrate your approach, or maybe what will hinder that?
I think so, and I hope so, especially since they're also sponsors of this session. What we try to create with this paper is to create this awareness that order is a very impactful cue, and currently it's very often ignored or maybe not exploited. And with that work, we wanted to create this awareness that it can and it should be used, and it has certain advantages, which we also try to emphasize with the visualizations in the paper.
Okay, so but you're using like powerful graphics hardware, right, to do this. Maybe this could be something that Tableau would not support on their side, or do you think that should be broken down more to some higher level programming abstractions?
The reason why we have this powerful computing hardware is also because we wanted to show that it's then easily possible to also do it in real time, so you can easily interact with it. You can adapt it. You can maybe in future even stream the data on the fly and then adapt the importance while you're actually receiving the data. So if you are doing all this on the GPU, you have way more freedom, and you can just like change and adapt the visualization on the fly. Maybe you're more limited with limited hardware.
Okay, so for the next question, do you think that the line rendering would also help to deal with edge clutter in graph visualization?
Absolutely. I mean, the examples that we provided in the paper are classic visualizations like time series or parallel coordinate plots, but that could of course be also applied to other visualizations. And if we get this awareness, then we can see that it could also be applied to, for example, graphs, because the idea there is you also have, as you said, edges that are intersecting with each other. And what is done there is right now they are, for example, bundled, but we could see this bundling as some sort of pre-processing step. So we then in the end come up with bundles, and then you somehow need to render these bundles as well. And then how do you do this, right? You could either ignore the order, or you can actively use the order to make the whole visualization way more expressive. So I totally see that.
Thanks. And maybe for the last question, I noticed some flickering in the lens. What can you do about it?
I think the reason why you saw this flickering is because when the way we implemented is when you hover over with the lens, we try to emphasize lines that are, for example, maybe currently hidden by other lines. And what we do there is we check for the line that you're, like, for example, currently occluding, that is in the center of the lens, and then we emphasize this line that is currently in the center. And if you then move the lens, then we of course then look for new lines that are currently in the center of your exploration. And instead of having maybe a hard cut between having a very high importance for this specific line and then reducing it suddenly, you could make this smooth so that it like is pulled forward and then like slowly moves back again. We also refer to this as like rubber band metaphor, that you have this rubber band and you smoothly pull it towards you and let it glide back into the visualization. So I think this could be done there.
Okay, so as I do not see any further question, I would say this concludes the session. Many thanks to all presenters for their interesting, really interesting talks. And also thanks for the audience for asking questions and posting comments. And one more time, thanks to Tableau for sponsoring this session. And I would be really interested to see if they integrate some of these approaches in their next version. It's been a pleasure sharing the session. Enjoy your lunch now and see you around. Bye-bye.